So I'm Damien Lebrun Grandier. I'm computational scientist at Oak Ridge National Lab. And so as he said, I'm going to give you an overview of Kokkos. If you have a quick question, actually, you may interrupt me. That's fine. OK. So this lecture, we're going to go over the main abstraction. We're going to cover the fundamentals. As he said, the long version of it, we usually do it over a full week. So I actually decided I'm going to hold all the exercises until the end, and we'll see if we have time. If we don't get to them, that's OK. You can actually find them. They're recorded on YouTube. You have the solution and everything, and more details that I could ever give you today. OK, and so there is a link here. You have my slides. If you lose a slide, you just Google Kokkos lecture, and you're going to find it very easily. So here on this slide, I'd like to recall the HPC landscape. So on the first line, you have today's landscape, so Trinity with Intel Haswell and Intel KNL. And so when you program for this machine, usually you would be using OpenMP 3. You have Sierra and Summit with Power 9 nodes and NVIDIA Volta GPUs. And you have Astra with ARM CPUs and Fugaku. And so you would use OpenMP 3 so for Trinity, Astra, and Fugaku. For Summit and Sierra, the programming model you would be using would be CUDA or OpenMP 5. For the upcoming generation, so you have several programming models that you need to be using if you want to target all the machines. There is OpenMP 5, CUDA, HEAP, or DPC++, depending on the machine. So Perlmutter at NERSC has Ampere GPU, so NVIDIA GPU. So you would use CUDA or OpenMP 5. For Frontier, that's about to come online, we have AMD GPU, so you would need to use HEAP. You could also use OpenMP 5. But for the upcoming Aurora, so you have yet another programming model, so SYCL with the DPC++ compiler. And so El Capitan is the same as Frontier. And so what I want to say here is that so the motivation for an abstraction layer like the ones you're going to see today is that if you really want to target all this architecture, you would have to implement several backends for your software, and not any code, the most performance critical code. So you may say, oh, but I see OpenMP 5 everywhere. Well, that's actually awkward because the different vendors at the moment, at least, they do not implement the same subset of the specs. So you would be restricted to a very small subset if you truly want to write some piece of code that's portable to all machines. And that's where so layers like the ones you're going to see today are very important. So here I want to convince you that it's why you should use an abstraction layer. So this estimate over there from the industry is saying so that a professional software engineer can write 10 lines of production code per hour. So that represents 20,000 lines of code per year. And so this software engineer here, it's not someone who writes paper and does all of other things that we usually do. It's really purely focused on software. And that seems low. I'm telling you, this is very, very accurate. Like I'm talking about high quality code that will be reliably used. So typical HPC application are today about 300,000 to 600,000 lines. So my colleagues in Sandia, they already maintained dozens of them in like this. We have some in Oak Ridge. These numbers are pretty accurate. And so to give you an idea, like E3SM is 1 million lines. Trillinos is over 4 million lines. So to rewrite if you wanted to port such a piece of software to another programming model, so let's say it worked on Summit and you were using CUDA and now you want to make it prepared for Aurora, a conservative estimate would be you need to rewrite 10% of your application. And this cost is huge, right? It means that switching the programming model would cost you multiple % a year per app. So this is really a huge cost. And every time, as I said, this is the performance critical part. You really need detailed, deep knowledge and understanding of how this programming model, or you can get performance from this from the programming model. So Kokkos, it's a C++ programming model for performance portability. So it's a C++ library that's implemented on top of programming model like CUDA, HEAP, OpenMP, C++ threads. We also have a SQL backend. And so the aim is to be descriptive and not prescriptive. I'll get more into detail later. And one thing that's really important to us, and we spend a lot of effort trying to make sure we align with the development of future C++. In fact, a good number of our team is part of the C++ International Committee. So another thing with Kokkos is it doesn't just come with a programming model. It goes beyond that. So it comes with math libraries that are based on Kokkos, so Kokkos kernels, we call them, math and graph libraries. We have also tools for debugging, profiling, and tuning. And we also have interoperability layers with Python and with Fortran, so some ongoing effort. So it's a truly open source project. So we have a pretty dynamic community. All the developments, there is no private thing. All the things we do happen on GitHub, and you can follow what we do. You'll see when we mess up. So it's really open. We try to discuss openly our design decision and get feedback from our users. So we have several hundred users at most institutions. So here, this little diagram is trying to explain the logic. And I mean, this would be the same for all the programming model, the C++ library you're going to see today. So you've got this application and software technology. So here, there are a few listed that are doing pretty well. So anyway, all this library, instead of themselves trying to target directly every single of the available of the machine that we want to target, they will use Kokkos, and Kokkos is the one that's going to be then mapping their code efficiently onto the machines. So here, an overview of the Kokkos ecosystem. Do you see my mouse if I move it? Yeah. So at the center, based on top, you have the Kokkos core programming model. That's what I'm going to present today. So we have abstraction for parallel execution and for your data as well. And so on top of it, then you have the math libraries and the graphs, Kokkos kernels. There is some other active experimental project with Pegas and even with giving you resilience. I won't cover them at all today, but you can, if you watch our lectures, you can see some. It's a newer part of Kokkos. We're very excited about that. Then we have all the tooling, which unfortunately I won't be able to cover much today, but this is one of the great strength of Kokkos. I mean, I started as a user myself, 5 years ago. This was one of the greatest thing in Kokkos. So the fact that there are hooks that are able to export information to different tools, whether you're using the vendor tools or whether sometimes it can be a bit awkward if you try to optimize some application over different architectures to get the same comparable numbers. You can actually write your own tool, or we have some that would be portable. And this is something that gets really important when you really have a production application. And then, so another big aspect is all the support we do. So we get specific funding from the Exascale computing project to support our users, so to focus on documentation, to prepare material for tutorials, to organize boot camps at all leadership facility, and to do continuous support for application and new user when question arise. And so then in yellow on top, so you have your Trilinos is one of the main scientific library at Sandia that had adopted very early Kokkos, but then you have all the software products, which would be what you will produce later, that build on top of that. One thing that I wanted to mention that was actually a great milestone for us is that the historical competitor of Trilinos, ATPESC from Argonne, actually recently switched over to Kokkos now to be able to run on GPUs, which was a really great victory for us. Like I wouldn't, if you had told me that 5 years ago, 10 years ago, I would never have believed that ATPESC would depend on a project that was originated at Sandia. So the team, so no, it's really so it's not, that's what I want to say, it's not just a Sandia product anymore for years now. So it originated 10 years ago or more as a project in Sandia and was early adopted in Trilinos, but now it's really a multi-institution project. So I'm in Oak Ridge, and I co-lead the project with my colleague Christian Trout from Sandia. And we have developers here in Argonne. We have people in Los Alamos, at NERSC. We have people even in Europe. And so here is so a summary of the team. The list is probably not complete, but I just really want to give you a feel that it's that's really one of the important parts. It's a large effort. So about so I told you, and it's actually myself when I started working on Kokkos, that was a really important aspect. We are very involved with the evolution of the C++ language. We want to make sure that application and software that use Kokkos now are going to be aligned with future C++. And so what we've been doing over the last years is we learn lessons from what we do in Kokkos and from what we think is representative of the needs from the HPC community. And we've been proposing some new feature for the C++ standard. So the first example of that's actually already in C++20 was atomic ref. That was proposed out of Kokkos. And so if you use C++20, now you can use it. I don't really have the time to get into detail of what it does, but it's some abstraction that we provide in Kokkos and that SQL and also Raja have. And so we really engage. I can't really speak for SQL, but we have colleagues from the Raja team with us on the standard committee. And so when things get accepted, then what we do is we actively we actually backport them down to the standard that we support. So atomic ref we have backported to C++11 at the time. Now we require C++14 in Kokkos, and we actually one of the excited news for this year that actually happened 10 days ago was we had proposed an abstraction for multi-dimensional arrays to C++, which was one thing that was really missing for if you're doing scientific computing. And I'm really proud to be able to announce to you that 10 days ago it was voted in for C++23. And this thing is really born out of all the experimentation we did with the Kokkos view abstraction that I will present today. And so MDSpan, so our implementation now is actually shipped with the latest NV C++, the NVHPC 2-chain. And so we backport it all the way to C++14 as well. And so what we do is then afterwards, we help our application transition. We want them to be using later just raw C++. So that's really something that's important for us. Now about the user community. I expect you heard a bit about the Exascale computing project, and so it's difficult for us right now. It's difficult to keep track of how many application users we can't keep up anymore with the numbers. But a sample to give you an idea in our community. So from ECP, in ECP there are 41 applications of software technology that use C++. 41, so within this 41, 20 of this project are using Kokkos. And these 41 include our competitor, Raja, and their users. So every other application or software technology that uses C++ in the ECP project right now rely on Kokkos to be able to run on Frontier or on Aurora. So now I told you about supporting our user and being really, really engaged with them. So we also have Slack, yet another Slack organization, right? So we have 900 members nowadays that are coming from, I don't remember the exact number, but it's over 90 institutions. And to give you an idea of the breakdown, so we used to be almost half were US labs. It's not true anymore. We're only a quarter are from US labs. So then they're represented from university and from, we have people who work for the vendors. We have people in Europe and whatnot. So here the graph on the right is so it's representing the weekly activity. So people who are connecting and who are actually connecting, not just registered. And so you can see that it's been pretty steady over the last 2 years. And we have daily over 100 people connected, and you have people posting all the time. So it's really a good place when you have questions. I encourage you, if you want to use Kokkos, to join and to get engaged with the community through it. So the online resource, so all our development is done on GitHub. We have an extended version of what I'm going to show you today online that you can find on our Kokkos tutorials website with so the recorded sessions for the training on YouTube. And here are information on how to join us on Slack. All these things you can really easily find if you Google Kokkos on. Anyway, so the first part that I want to tackle, one of the fundamentals in Kokkos, are data parallel patterns. So I want to show you how you pass computational bodies to Kokkos at runtime, how this work is mapped to execution resources, and I'm going to present to you two main parallel patterns, parallel for and parallel reduce. There is also a parallel scan, but I won't cover it today. There is a simple example we can go over. So here, let's consider this example. Assume you have some number of atoms, n, and you want to loop over all of them, and you want to compute some force onto all these atoms. And so you do a loop with a counter, so a counter which is the atom index, and you calculate some force. And so we're going to see how Kokkos maps work to execution resource. So each iteration will be a computational body. It's a unit of work. You get an iteration index, so here atom index, that identify a particular unit of work, and a range. So the range here would be 0 to number of atoms. So you give this iteration range, the computational body, to the kernel, and Kokkos decide how to map that work to execution resource. In that computational body, without getting too much into details, you cannot make any assumption of how we map it. You're not allowed to use your own unsynchronization in it. But yeah, that's so. So let me show you how you define such computational bodies. In a bit, if you're lost, I know you've seen OpenMP in greater detail a few days ago, and I have a few examples that shows parallel. So I hope you don't feel lost. So functors in C++ are function object, so it's a very, very common idiom in C++. So here you have an example. You have a struct that is callable. So the operator parenthesis means that you can create an object, a function object, and you can call it with the parenthesis operator. And you get work assignment. And so inside, what you do when you implement your functor is you implement the body of this function here. So how is the work assigned to function operator? So here is a syntax for Kokkos. So you would call Kokkos parallel for. You define your range by giving the number of iteration. It's actually a shorthand. There is a bit more complex syntax that you'll see later. And you give your functor, the computational body. And the work items are going to be assigned one by one. And so here the functor take an index. And so here is what I was trying to tell you. So the concurrency and ordering of parallel iteration is not guaranteed by the Kokkos runtime. So if you're familiar with the C++ parallel library, it will be parallel unsequenced equivalent. So you cannot make any iteration, assumption on what order the work item are going to be executed. And since you don't have any guarantee of concurrency, you cannot do your own synchronization mechanism. So here, getting back to our picture where we were computing forces for all our atoms. So if you were writing a functor, you would define a struct atom force functor. You would have as a public data here something that stores the forces. Then you would have this other something that has useful information to do the computation of the forces, the atom data. You have a constructor here that takes the forces and the data. And the computational body is defined here. So with the operator parenthesis, you take an index for the atom. And so what you do is you compute the forces for the index that passed to you. And you call this internal function that you define somewhere, calculate forces, and you get your data. That's how you would pass the data to the functor. Yes. So this writing functor like this is a bit tedious, and C++11 came with a great abstraction, which are lambdas. So here is the same function, but written with a lambda. So here's this. So I don't know how familiar we are with C++. So this is a capture clause, and it says that. It tells that the lambda is going to capture things by value. So this is really important in our semantics. You must be capturing by value, because potentially the computational body is going to be sent to the GPU. We'll get more into detail later. So one thing I wanted to say is lambda are not magic. It's really just the compiler generating the functor that we saw before for you. So yeah, that's what I was telling you. For portability to GPU, you must be capturing by value. You cannot do it by reference, because think about it. Otherwise, if you capture your atom data and then send the computational body to the GPU, well, you're referring back to host memory, and you're going to have memory access violation. Another thing that's important to understand, so even though you can't, if you're writing portable code, you can't be using stud vectors. But so if you're not you're not familiar with C++, that's standard containers from the C++ standard library. So if you were capturing it here, concretely, it would mean that you're making a copy inside your computational body, which means that whatever you do inside the body, once you exit, it gets out of scope, and you did the computation on the copy, not on the actual data. And so that's why you will see later that Kokkos gives you an abstraction for data. Similarly, I know Raja will present you some abstraction for the data as well. So now, how does it compare to OpenMP, which I expect now you're a bit more familiar with? So on top, you have the serial version, the initial version. So you have a for loop with an iteration range from 0 to n. So with OpenMP, you would write this directive, pragma OMP parallel. And so you just annotate, basically. And here it's how the same thing would look like with Kokkos. So you spell out parallel for, you have the bound of your range, and you have, here we're using a lambda. So conceptually, it's no more difficult than OpenMP. Just the annotation are going in a different place. And one thing that I personally think is a great strength is it's really using natural C++ construct to express that. No directives. So here I'm going to do a small example where we're going to try to integrate the space under the curve, and we're going to approximate it, if you're not familiar with it, with rectangles, basically. And we're going to try to use Kokkos to do this integration. So here is the serial implementation for it. So we're going to compute the total integral in this variable total integral here. We are looping over all intervals that have been defined here in blue, and you compute the contribution of each. So the area of each rectangle, and you add it into total integral. So now the question is, how do we parallelize it, and how do we do it correctly? So the pattern. So here we see it's a parallel for, maybe. No, I mean you'll see. So what's the correct policy for that? So the body is in blue. So we're going to try first attempt. We're going to slap a parallel for on it. So over the number of intervals, and I'm doing what I told you. I'm putting the computational body into a lambda. So this first example is not going to compile. There's a mistake, which is, so here when you do that, you're capturing total integral that's being used here into the lambda. And what C++ does, it's because it's captured, it's actually going to be const. And it's actually a good thing for you because it's treated as const, so you're going to see immediately that that doesn't work. So the problem is you would make your own copy of total integral. So if you increment it in the computational body, it's not going to work. So let's do another attempt. So we're going to use pointers. So I define the total integral, and I define a pointer to it. And so then I try to do this integration. So for the moment, for the sake of the exercise, let's not even think about memory access violation, because if you send that to the GPU and your address is on the CPU, you're going to have bad surprise when you execute. But here, conceptually, what happens if you do that? So the problem with this implementation, so here when I add the contribution, I'm referring to the original memory address. So I suppose you've already been discussing race conditions. So the problem here is that what's going to happen is you're going to have one thread that's going to read the current value of total integral, and that's going to start doing some computation, and the other one is going to read the same value, and then they're going to write the solution, but they don't know that someone else had it. So the problem is that you're using the wrong pattern. Instead of this, you really want to use a reduction. So the important concept, so this was really a reduction. So you're combining all the results contributed by the parallel work. So in OpenMP, I expect you've already seen how you would do that. So what you are supposed to recognize when you do this, you compute this, is that the real pattern is not a parallel for, it's a parallel for reduction. And so what you would say in OpenMP is, I want to reduce the final value into that variable, so you need to annotate it. And so that's how you would do it with Kokkos, and with OpenMP. And how do you do it with Kokkos? Well, if you're familiar with OpenMP, it's very similar, right? So we have a pattern, parallel radius. You have the bound like you've seen, and so a functor, and you pass the final reduced value as a trailing argument. So that's where you want the result to reside at the end. One subtlety, though, in the computational body. So here is, again, just a copy of what we had before, how you would do it in OpenMP. So now, remember that functor that we had on a parallel for in Kokkos? It was taking an index that was telling you which atom you're computing. So here you get another argument that tells you it's a local variable where we are accumulating. And so what you do is you take it by reference as training argument, you add to it, and then Kokkos internally does the reduction. And you get your result in total integral. So the second argument, it's a thread private value that is managed by Kokkos, not by the final reduced value. And so how we use it is depend on the backend. Often like I suppose you've seen in the exercise in OpenMP, we can build a tree behind to do the reduction. But these are internal details of how we implement it. So now I've shown you already, I've given you an overview of how to call a parallel for and a parallel radius. So an important comment here is always name your kernel. So on the first call that I was showing you, I was doing parallel radius and giving the range. There is actually the ability of pass a label as first argument. And I want you from the beginning, when you use Kokkos, to get used to it. I guarantee you, if you don't do it, you will regret it later. What we use it for is we export that label to tools. And so when you use some tools like Tau or whatnot, today they are actually able to talk with Kokkos and realize how you annotated your kernels. And so when you're going to look at the profile, or try to debug, I guarantee you'd rather see the label that you wrote rather than the mangled name that your C++ compiler generated for it, especially when you're using lambdas. So yeah, please name. One good habit that you will see in application of software technology that use Kokkos is they even prefix their labels with the name of the project. because I've gone to help. I've been to a hackathon trying to help application and looking at profile, and someone is going to tell you counts or offsets, and that's great. There's probably through the entire software stack there is probably every single library has counts and offsets. So try to label your kernels. So now we're going to do I guess I'm just going to tell you about the exercise, but I'm going to keep moving. So this exercise would be computing an inner product between a vector y and the product of the matrix A with a vector x. And it's an example that we reuse throughout a number of exercises. And as I said, we're not going to tackle this exercise right now. Even if at the end, if we don't have enough time to do it, don't worry. It's the solution is online. There is recorded my colleague actually doing the exercise. So, but actually, since there is not more than that, I'm just going to move on. But we're going to get back to it several times. So every time we're doing a scalar product of vector with matrix and vector. So I'm going to move on. Yes, I'm not going to comment on that. So summary of this first initial section with the parallel pattern. So what I want you to remember is that the most simple case usage are very similar to OpenMP. And the advanced features are not that much more complicated. Just the annotation, as you've seen, go to different places. It's pretty natural when you start playing with it. There are three common data parallel patterns that we support. There is a parallel for, the parallel reduce that we've seen, and the parallel scan. Parallel computation is always characterized by the pattern, so for, reduce, or scan, the policy, which I didn't get over yet. All the one you've seen were what range policy, and the computational body. And the user job is to provide computational bodies to Kokkos as functors or lambdas, which can handle a single work item. Okay. So now you had an overview of data execution. Now I'm going to talk about some of the main abstraction we provide for data, which is really important. So in Kokkos, we call our abstraction view. And so the goal for this is that you get a good overview of how this Kokkos view works. So let's look at this motivating example. So we're going to do a vector add on the GPU. So the first block here, we're using a lambda version. So you have some array that's allocated here on the CPU. We also allocate y somewhere. And we do a parallel for. We pass a label, so we're doing ax plus y, then a range from 0 to n. And here is my computational body. And so I'm doing the computation. Here is how it would look with a functor. What's my problem here? Well, this data, these arrays, x and y, they've been allocated on the host. So they reside on the CPU memory. And so if you execute this code on the GPU, you're going to get memory access violation. So how would I fix that? So you need a way of storing data. And so very commonly, you'll see we need multidimensional arrays, which can be passed to a GPU. So that's a motivation for views. So the Kokkos view abstraction, so it's a lightweight C++ class that has a pointer to the array, so it knows where the array lives, and it does something else. It has it has some metadata, and I'll get into detail in a moment. So the high-level example that we saw before is you would declare a view where the data are double. So double star, it says that you want a view of rank 1, so one-dimensional array, x and y. You would have some logic to populate them, and then you would do your parallel for. So view, so remember what I was telling you, you see the capture clause, they're captured by value. So it's being copied, but the view abstraction in Kokkos has reference semantics. So when you do a copy, a C++ copy, it's actually a shallow copy. So you're copying the metadata, not the actual data. Kokkos will never do, unless you explicitly ask for it, will never copy your data. So less bad surprise with performance. So view are like pointers, and so here we encourage you, even in your functor, to just copy them. Don't do a reference to the original view. So the view of a view, so it's a multi-dimensional array that has, so it can have dimension 0, which rank 0, which means it's just a scalar. But we support in Kokkos up to rank 8. So rank 1 would be a vector, rank 2 would be a matrix, etc. The number of dimensions, the rank of a view, is fixed at compile time. All the arrays are rectangular, they are not ragged. The dimension along, so the extent along each dimension can be set either at compile time or at runtime, and you can mix both. And when you want to access the elements, you use the operator parenthesis. So I'll show you a few examples here. So the first one, we are declaring a view of rank 3, where every single extent is dynamic. So at runtime, I'm passing n0, n1, n2, that are the dimension. The second example, I know n2 at compile time, and so I'm telling Kokkos that I'm taking advantage of it. And so when I construct, I'm passing the 2 other dimensions to Kokkos, and so on. And in the last one, I don't pass any dimension, I just pass the label. I just pass a label, and that's it. So the way you access, sorry, I'm not sure how to, bad idea. So I apologize about this thing, I don't know how to remove it. Sorry. So the access, you pass index I, j, k, and that's how you access the element. And here what we're doing is we're assigning a value to the element. One important thing to note is that the runtime dimension must come first. And it's not a limitation from Kokkos, it's really a C++ limitation. So important thing with Kokkos, so allocation will only happen. Actually, let me go back for a second because I don't know if I have a slide for that. You remember how I told you, please label your parallel construct? We similarly, so the parallel construct, it's optional, but you really should do it. For the view, you don't have the choice. You must give a label. Same thing, really useful when you're keeping track of memory with tools. And same tricks, think about prefixing it with the name of your application. So about allocation, Kokkos does not do, so I told you we don't do hidden copies, we don't do hidden allocation. Like, it's always explicit in Kokkos. When you copy a view or a sign, so all the copies are shallow, like pointers. If you pass view by value, so we encourage you to pass them by value. I was telling you the view is conceptually a pointer to the data and some metadata. So part of the metadata is going to be, we do some reference counting. So it is conceptually a bit like a share pointer, a stud share pointer. So if you're not familiar with C++, this is one of the smart pointer in C++. So when you construct your object, we allocate, and then so we automatically keep track of how many of the shallow copies that you have are in flight in your program. And when the last one goes out of scope, then we deallocate. We actually deallocate the memory that was allocated. So we take care of this for you. The rest of the metadata for view we'll see in a bit, but essentially it's things like where does this, it's compile tile information, like where does this allocation reside? Is it on my CPU or on my GPU? And things like the layout of the data. And we'll get into detail in a bit. So here a small exercise to understand a bit the fact that they are shallow, the copies are shallow. So assume I define two views with one runtime dimension and the second one compile time 5. So the first one, I'm labeling it as A, and assume you have a runtime value n, and then B, label B, and with a different runtime dimension. So A is n time m, and B is k time m. So here in this first line, what I do is I assign B to A. So what it does is it makes A become an alias to B. At this point, the initial allocation n time 5, there is nothing pointing to it anymore, so we deallocate it. Okay. Then we define a new view where both dimensions are runtime dimension, and we make it be a copy of B. So C also points to B. And so assume in your code you're doing it somewhere where you can actually access the value. If we assign through A1 to the element 0, 2, and then to B we assign 2, or to C we assign 3. The small exercise is what would be printed if I looked through the view A at the element 0, 2. So I told you they're all shallow, and we all made them point to B. So they're all the same, aliasing the same memory. So what we did is we wrote 1, we wrote 2, we wrote 3. So what would get printed? 3. So about the view properties. So accessing view size. So if you want to access, when you get handed a view, if you want to access its extent along some dimension, you can use the extent member function. So if you have a view like here, you can do that given to you. Let's say you don't see how it was constructed. You just know it's rank 2. You can ask for the extent along dimension 0 or along dimension 1. So since we support also compile time dimension, when there are compile time dimension, you can access them at compile time if you need it via a static extent dimension. This is more advanced. You probably won't have to mess with it for a while. And you can retrieve the row pointer to the allocation via the data member function. And you can check its label via the label member function. So one thing I didn't really cover here, but it's more advanced, is why would we in the first place care to have compile time, mixed compile time and runtime dimension? Well, if you really know at the time you write your program what the dimension is going to be, if you spell it out, you're actually giving an opportunity to the compiler to optimize away all the index offset calculation. So it's kind of a big deal. If you know it, you should definitely tell Kokkos. And so here on this small example, we create a view that has runtime dimension that we set to n0 at runtime and 5. And so what you can see is you can verify at runtime after construction that the extent is in 0. The extent along the second axis is 5. So this construct in C++, if you're not familiar with it, it's something that's actually being checked at compile time. And here, we're verifying at compile time that it's 5. So it can be useful when you do compile time calculation in your program. So here we check that the allocation happened. It's not, the pointer is not null. And the label is the label that we passed. OK? So here is where we would normally look at a view. It's just essentially, we might get to it at the end, looking back at the first problem, and instead of using pointers, starting using views. And the first example, the first exercise, if we get to it, runs on CPU. And by using view, we start being able to run it actually on the GPU. So now, we covered the parallel construct. We talked about the Kokkos abstraction to store data. Now I'm going to present to you two very important abstractions in Kokkos, the abstraction execution spaces and memory spaces. So execution space, a very, very high level, it just tells you where the code gets executed. So this scheme here is how we like to think of a node in Kokkos. And so in blue here, you have potential place to run the code. So you have cores on the host. And if you have GPUs, you potentially have several accelerators that we could be using. In Kokkos, so we have multiple concrete execution spaces that are available to you. The first one would be, the simplest one would be serial, so run on the host in serial. Then we have parallel host backends that you can select. So you select them at compile time. You enable them when you compile Kokkos. So we have one that now use C++ threads. We used to use POSIX threads, but we recently in Kokkos 3.6 moved to use directly the native C++ support for threads. One of the motivation to change was support on Windows. So we support OpenMP 3 specification via the OpenMP, so it's to run in parallel on the host. And then we have an abstraction to run on NVIDIA GPU, so CUDA. So heap in Kokkos, I don't know how much you know about heap, but technically you could use the heap programming language to target either NVIDIA or AMD GPU. In the Kokkos world, when we say heap, we are specifically targeting AMD GPU. We don't let you target NVIDIA GPU with it. And so we have other execution space. We actually have one called SYCL, where we actually use the SYCL library to target Intel GPU. So in Kokkos, when you see SYCL, we exclusively using for Intel GPU. And we have an OpenMP target execution space, which is OpenMP 5 that you might have, I don't know what you guys covered in OpenMP, but I assume you saw some of it. So that's how we use underneath the hood OpenMP 5 to target the accelerators, the GPU. So now, getting back to this parallel for construct. So before, you had seen the shorthand syntax. So you were saying, I want to do a parallel for, pass your labels, and you were just telling how many iterations you want to do. So this is actually a shorthand version for spelling out, I want to do a range policy. So it's an execution policy in Kokkos. You don't pass any execution space which default to use the default execution space in Kokkos, which will depend on what you enable. So if you enable Kokkos to run with CUDA, by default, this shorthand means I want to iterate from 0 to n on the GPU. So in libraries, when you really want to have fine-grained control, you will often spell out everything. This syntax gets really, you get used to it very, very fast. The shorthand is nice, for example, or for small code when you prototype stuff. And then the body doesn't change. So again, the execution space is really how you tell Kokkos where to execute. So it's passed as a template argument to the range policy. So the requirement to enable for enabling execution spaces, so you must compile, as I mentioned before, with the execution space enabled. So at the time you install Kokkos, you configure and you say, I want to use this backend. The execution spaces must be initialized and finalized. You don't explicitly initialize an execution space. What you do in Kokkos that you would have seen in the exercise, but you need to initialize the Kokkos runtime, and then this is taken care of for you. And at the end, it's a bit like MPI, right? You want to, you need to, before you start using any MPI construct, you need to initialize the MPI environment. So same thing with Kokkos. You need to initialize it, and when you're done, you need to finalize it. So function. So one thing now that we had at the moment, we were, for simplicity at the beginning, I was using the capture directly in C++. So in practice, when you want to be able to write generic code and you want to run on GPU, you will need some annotation depending on the programming model behind. So what we really do in Kokkos is we provide you macros that you must annotate your computational bodies with. So for function, you have a macro called Kokkos function, and for lambda, you have Kokkos lambda. That's simple. It's no magic. Underneath the hood, what we do is if you enable CUDA, we do the proper host and device annotation. I'm pretty sure the Raja has the exact same mechanism. So here, the person that did the slide did so we have Kokkos function and Kokkos inline function. So inline function just add inline to it. Here, just a note, it's not strictly necessary because if you define it in the body of the function by the C++ language, it's implied that it's inline. But anyway, so one addition to what I told you before, and we didn't want to overwhelm you immediately. So your function, your computational body needs to be annotated with these macros. And so here, similarly, the Kokkos lambda, so we're only doing CPU. This is what you've been seeing on the slide before. And if it was GPU, you would need device and host annotation. So when you annotate with Kokkos lambda, you're guaranteed that it's going to work on any of the backends that we support. We're going to inject the correct annotation. So that was about it for execution space. So again, that's controlling where you wanted your computation to be done, to be executed. So now about memory spaces. So that's how you control where your data is going to live with our view abstraction. Memory spaces, so they're explicitly manageable memory resources. So here, going back to our node, you could have some unpackaged memory. You could have some DRAM, some non-volatile RAM. Same thing on the accelerator. You have some memory that might only be accessible from the GPU. So every view. So I was telling you about the metadata on a view store. Its data on a memory space, and the memory space is set at compile time. So the syntax I showed you before was just a shorthand again, just to make things simple, but really a view always has a memory space. If you don't spell it out, it's just a default, which is going to be the default memory space for the default execution space that's enabled. So the available memory spaces that we have in Kokkos, we have one host space, which is pretty descriptive, right? It's memory that lives on its CPU memory. CUDA space is the memory on NVIDIA GPU. CUDA, what we call CUDA UVM, so the name stayed, but so unified virtual memory. Now the CUDA refers to virtual memory. It's page migrated memory. So when it's a special allocation with CUDA where when you start accessing some location, the CUDA runtime detects that you're accessing it, and it starts migrating the page over to the GPU. So you pay a cost initially to migrate that data, but if you keep having a bunch of kernel on the GPU, you won't actually be able to tell the difference whether it was normal GPU memory. It's something that's usually a recommended transition path when you want to, if you never worked with GPU, because it's a memory space that you can access both from the host or from the GPU. And so all the other execution space have their memory space. So you've got a heap execution space that has also heap space. They have more abstraction. I won't go too much into details of all the fine grain that we have, but basically, if it exists in your programming model, we have something equivalent in Kokkos that you can use. And as I was saying, so each execution space has a default memory space, which is used if the space provided is an execution space. So when you do, you could technically create a view by passing CUDA, which is an execution space, and we will deduce that you want to use the CUDA space. When no space template argument is provided, we use the default memory space of the default argument, execution space, as I said. So, which means that what you saw in the previous example, double view of double star, so a view of rank 1 with runtime dimension here past n, is really default execution space is an alias that results here into, so it depends what you compile. If you compile for CUDA, it would be CUDA space, and CUDA memory space would be CUDA space. So that was here for the shorthand. So now let's go again about some of the details. So assume you have a CPU and GPU. When you declare explicitly a view of rank 2 here, the double star star, that live on host space, and you call it host view, and you pass it some constructor argument, label and dimension and whatnot. There are some other arguments that are beyond the scope of the training, but when later you get obsessed with performance and you don't want to pay for anything you don't use, you have the way to take Kokkos. I do not want to initialize this view. Things like that. I don't want to pay for the cost of, because I know I'm just going to assign later. Things like that. So anyway, yes?
We got a question in the Slack saying that right now view are more like, as you say, the share pointer. You can have, it's loading and you can have multiple view of the same.
Yes.
And they were asking if you have like a unique pointer kind of a view.
No.
No.
No. So here so assume you're in the, so it's representing your CPU memory here, and so that's what would be what your view is, and it really has, so in yellow it has a pointer to the original data, and what this is showing you is that the data here lives on the host because you said host space. And so with CUDA space, okay, just about unique pointer, the semantics would just not work at all not with Raja, not with Kokkos, when we SQL, because remember, when you want to dispatch something on the GPU, we have to capture by value, which means making a copy of it, delete it. Like if you would have to move, which you can't do. You can't move into the body and send it. So it would be destroyed by the time it's dispatched. So it's just not a thing, unique pointer. It's a good question, but you can't use it. Okay. So back to this. So here on the second one, where I explicitly said CUDA space. So my view object I created here on the host. And so this metadata has a pointer that points to the GPU memory. I mean, what it means is that when I have this view, the second one here, on the host, if I try to access elements on the host, it's going to be a memory access violation. But this can help you conceptually think where that this template argument control where the data is being allocated. So here, let me remind what it is. So we are going to try to do a summon array on the GPU. So we are allocating a vector, so rank 1, so a vector that we call array of size. And so what we do is, so this code, I guess we're going to need to update it. So it's a first attempt. The first loop that you see here is populating this loop on the host. And the reason why it was written on the host is because you actually needed to read from a file, for instance. And then, so we are doing a reduction. We are summing all the elements in it. And we explicitly saying that we want to do it on the GPU, right? And so the problem with that code here is, you remember I was telling you about memory access violation? So this attempt to access on the host some memory that actually lives on the GPU. So this code would give you a sec fault at runtime. Actually, we are a bit nicer than that. We would give you a message, tell you you're trying to access the view array from the host, and you don't have access to it. But it would literally, it would crush your computation. So now, second attempt. So let's see what this thing does. So it allocates, so it says, oh, I need to allocate on the host. So let's allocate on the host. So here this time, this is fine, right? It lives on the host. But now I'm running on CUDA. And from the GPU, I'm allocating something that's on the host. Well, that's not going to work very well. Same thing here. So here, it's interesting. It's something that I reworked to improve error message lately. And so here, we're also going to warn you. Kokkos is going to tell you what happened. You're just not going to get a sec fault. The truth is the error message quality cannot be as good without too much cost. Because I detect that you're doing an illegal access, and I'm telling you, but I cannot actually look at the host, the label, because the label lives on the host. And there are ways we could enable it, but you probably don't want to pay the cost to have that. So what are the solutions then to make this code work? You have several options. So you have this CUDA UVM space, so this unified memory, or virtual, yeah, no, it's UM, not VM now. So the unified memory, so the page migratable memory from CUDA, that would be a solution, sure. The performance, I mean, you probably don't care that much about performance if you're reading from a file and if you're just doing just a single loop, but it would be, the cost you would pay initially to migrate the data is not great. This is another abstraction so host pin memory, it's host pin memory in CUDA. If you're not familiar to it, so this one is page migrated. The runtime detects that you're going to access it and move it to the GPU. And there's a cost associated to it. The other one is zero copy direct access through the PCI or whatever you're using. So you're accessing them one by one, you don't copy. It's going to be terrible, the performance on these loops, but it's going to be legal. And in some patterns, if you just occasionally access some value, that might actually be the right solution for you. Unfortunately, it's not something we can really go into depth during such a training. But so the other solution, the last solution, would be mirroring, which is explicitly creating a mirror on the host that you may access. And let's see how it goes. So mirror are views of equivalent arrays that are residing possibly in a different memory space. So when you're going to create a mirror, that's what you're going to do, create a mirror on the host. Okay, I'll get to it in a second. So let's see the syntax first. So assume you have a view type. So it's just an alias for a rank 2 view here that live in some space. So you create it. You can create a host. You don't actually have to spell that out in C++. You could say auto host view equal Kokkos create mirror view of view. And it's actually great. So what it does, so here, assuming that you had a GPU and space was the GPU memory, when you create a mirror view, the host mirror is going to be here, and so there's going to be an allocation. So the cool thing with create mirror view is, what if I was just computing on the CPU anyway? Do I really want the copy? Well, because you said create mirror view, not create mirror in Kokkos, it's going to point to the original data. It's actually going to be a handle to the same thing. Remember, Kokkos doesn't do any, any implicit copy. So when you said create mirror view, is give me something I will be able to access into the new space. So here, when you don't say what the new space is, it always means the host. And allocate if you really need to. But Kokkos will never surprise you and allocate. Here is you're telling Kokkos allocate if you really need to. And if you want to access data, then I'm told you never no implicit allocation and no implicit copies. You want a copy, you will have to spell it out. And there is actually, that's not what we need in the pattern, but there is also a shorthand. You could say create mirror view and copy if you really wanted to. So now we created the view, the host mirrors, it's the same thing. So now in the pattern we had, so important thing, we haven't seen layouts yet, but Kokkos, really when you write Kokkos, it's really device-centric. So the way you would proceed is really you would create the view that you want on the device, and you will mirror it on the host, not the other way around. It doesn't actually matter if you're doing one-dimensional, but for higher ranks, it would have potentially consequence on the layout that you mirrored. And so when you create the view directly on the host, you already pick the default best possible option for the layout for your device. So you create it on the device, and you mirror it on the host. So in the initial program that we saw, you populate it, and then you do that copy. So the deep copy, it's like CUDA mem copy, the syntax. The first argument is a destination. The second one is a source. So here you're saying deep copy the host view onto the device view. And then you would launch your kernel that was doing, in the previous example, a reduction or whatever you would want to compute. So in your computation, assuming you need to, I don't know, checkpoint or something like that, you want to copy back to the host, you would have to explicitly then later copy back. So the memory you manage explicitly, you get used to it very, very quickly. This initial learning curve is really worth it. You don't need to be even smarter later when you want to get just acceptable performance. We force you to think a bit about where is your data and moving it. And ideally, you're going to populate it on the device already, and you're going to do everything on the device and migrate less and less. Here it's showing you what I already told you, which is, hey, what if my space was already host? Well, we only allocate if it's not accessible. If you want a pattern where you actually wanted an actual copy and duplicate, in the Kokkos terminology, you said a create mirror, not mirror, view. And so that's what I was telling you. We never do hidden copies. Okay, so I'm going to glide over the...
Yeah, we have another question. It's like in parts of space, you show you put CUDA in the slide. So how it works if you want to write a portable code to go for the
that's a really good question. In practice, I never spell CUDA. There is a Kokkos default execution space, which aliases to what Kokkos was compiled for. So when you, it really depends who you are using Kokkos, right? We don't have just one profile. If us here in the training, we're gonna just use all the default and probably not say anything. If I'm a library, I cannot make any assumption, and I always have to take it as a template argument and have my user spell it out for me. On an application, you know what are your targeted platform, and if you want to target everybody, you're going to use these aliases. If you target explicitly only one and you felt like spelling them out, you can.
So does space have more capabilities or something like that? For example, does the space I have a little more intrinsic, and if I use the default view, I lose a little bit of this kind of.
So for memory spaces, right?
Yeah.
So that's another really good question. So for all the backends, you're going to always have so CUDA as CUDA space, heap as heap space, and so on. OpenMP target as OpenMP target space. So this one is always memory on the device. This always work. You can, and it's conceptually that's the memory that's accessible from the device, the normal memory. And this, if you don't want to spell out from execution space, you get the memory space. That's how you would do it in generic code. In CUDA, even though I'm not covering too much into depth now, I told you we have an abstraction for so page migrated, so what we call unified, is it unified? I'm always confused. Yeah, unified memory in CUDA. And you have host pin. In heap, just the same thing, heap host pin. And we recently added, it's going to be in Kokkos, it's in Kokkos 3.7. We have another abstraction for migrated data. And similarly, SQL has its own alias. So if you don't, it's a bit awkward, to be honest, at the moment, if you're actually working with this page migrated thing, because they're not necessarily supported by all models. So if you're using OpenMP target, we can't provide something like that at the moment. But it's something we're actually working on right now. We are working on some providing compile time ability of finding out if this exists for the execution space that you're working with and getting an alias to them so that you can write generic code. And it's something we were literally talking about that over the last month in meetings, and so it's coming soon. Okay, so summary about what we just saw. So I presented to you the main, very important abstraction for Kokkos. I mean, if you remember only two things today, Kokkos provides you abstraction for parallel execution and for data. And so the abstraction for data, we call it Kokkos view. If you want, about the name, if you want to hear what I think about our name, just buy me a beer and like view it's the name we use, Kokkos view. But so that's conceptually it's a pointer to a multidimensional array that reside in some memory space. Again, with that reference counting I told you about. It's abstract away platform independent allocation and does automatic deallocation via this reference counting. And handle the access. So the heterogeneous nodes have one or more memory spaces. We just briefly saw the mirroring, and that's what the example would be about here. Basically, we would solve the example you saw. We would explicitly do the data transfer. Heterogeneous node, you will have, so you always, by default in Kokkos, if you enable device backend, you always have a host backend. And you have an alias actually for that. You have the same way you have default execution space, you have default host execution space. So you always have something enabled, and if you don't know what's enabled, you can use this alias. And so you can without getting too much into detail, you could technically have in a build of Kokkos a serial backend, a host parallel backend, and a device backend. But at any time, you guarantee there is at most one. And so you have control. You have control over where the code is executed via these template arguments on the execution policies. That's where you pass your execution space. So we talked about where the memory lives, but if you really care about performance, that's not all. Access patterns are going to be a really big deal. And so the learning objective for this small subsection here is introduce the view layout parameter in Kokkos that control how the data is laid out in memory. And we'll see how this has tremendous impact on the actual performance of your kernels. We're going to see how the access pattern result from how we map the work and how essentially the default in Kokkos you need to understand a simple basis rule, but then we choose the best default. But we give you further control if you have a good reason and your access is not usual. Anyway, so I'm gonna briefly give you an overview of why these access patterns have so much performance impact, even though I suspect you probably had other classes covering that before, I hope so. And then we see a concrete example of the performance when we use different configurations. So let's get back to our example where we are trying to compute dot product between y and a applied on x. So it's that inner product. So we are doing the parallel construct in Kokkos, the parallel reduce, passing a label. We're spelling out here range policy. Some execution space is the template parameter. From 0 to n, and so for the reduction, remember your work ID, and here the thread private local variable where I'm gonna compute my contribution, add my contribution. So here we decided to parallelize over n. So we are doing, so inside the body, the index you get is your row index. And so what we're doing is we are computing dot product for each row. So for this row, so the computational body is you loop over m, and you compute ax, and you do the dot product, and you add your contribution into the last thing. So the main question is how should the matrix be laid out in memory to get good performance? So Kokkos has that are the two main layouts. I mean, there are more, and you actually have the ability to define your own if you really want to. So there is layout left and layout right. So layout left is the one that has the leftmost index, which is threaded one in memory, and the rightmost is the rightmost that's threaded one in memory. So if you were going through indices, so that's how you would go over the matrix. So it would be also in 2D, sometimes we refer to them as column major or row major. So the layout that I didn't introduce yet, so is a template argument for views that you must set up at compile time. It's optional. If you don't say anything, what Kokkos does is it picks one for you. Picks one that's probably going to work well for you. But if you specify it, one thing that's important, I don't know if we're going to have it here. So if you specify it, it would be the second argument. So you can omit space, but if you're specifying both space and layout, it must come first. You'll get a message that tell you it doesn't compile, but just saying. So the most common layouts are layout left and layout right. There is layouts threaded, and there are some of our very advanced applications that or software technologies that define their own layouts. But this is not the easiest exercise. It's going to become actually much easier to do with the transition to the MD span that I mentioned that's being merged into C++23, because we learned from what we did in Kokkos and we designed for easier way of easier customization point to write your own layout. Anyway, so as I was telling you before, layout left is the leftmost index is stride 1, and layout right is rightmost index is stride 1. So what it means is for layout 1, if you go through a row, so through the row, they're in. Okay, let me straight back. We'll see in a second. If no layout is specified, so we use a default. With the default, so for CUDA, what we pick, it's not just CUDA. For GPUs, we pick left, because as we'll see, that's the best access you're gonna get. And for host, we get right. So layouts, you can write your own layout. That's what it's saying. And we have layout stride is in Kokkos directly. Okay, actually, what's up? So this exercise is doing the dot product. I'm just gonna go quickly over the result for you. So in red, there's our Pascal NVIDIA GPU. And so here on the x-axis, we vary the size of the row. There is some it's total size, so we change the dimension of the matrix shrink. But so the total size is fixed. But here you have the number of rows, and we look at the bandwidth as a measure of performance. And so what we see. So on the Pascal generation GPU, but the trend would be the exact same thing if I ran it on Volta or Ampere. You see that in the problem, the exercise that we're doing, that we are looking at, the dot product, the performance is, so you reach a bandwidth of close to 600 gigabytes per second with the left layout, and you only get 150 or so for the layout right. On KNL, the layout right reached over 300 gigabytes, and the other one is, I don't know, 10, 20 gigabytes. So it really shows you that your choice in terms of layout is gonna, so it's the same thing on as well. Your choice of picking the right layout is giving you at least an order of magnitude of performance difference. So the question is, so that we observe it and know why. So now we're gonna see what I tried to explain to you earlier, and it was a bad idea. But so the notion of caching and coalescing. So about thread independence. So here you have the computational body that you pass to Kokkos. So the question is, once the thread is reading, the question is, does it need to wait or not? And so CPU threads are independent, totally independent. And so your best bet here is going to be that a thread has in cache the next location that he wants to read. The GPU threads are executing in a synchronized fashion. And they have a shared, the cache that they have, line cache, they access it together. So you want consecutive thread to read consecutive address memory. So it's called coalesced, which I hope you've seen before. Because I actually don't remember if I have much more on this. But so in particular on GPU, if you use a warp in the CUDA terminology or wavefront on AMD GPU with heap, they must finish their load before any thread can move on, which means that if you're not accessing the same the memories that are in cache, you'll have a bunch of threads that are inactive, so it's very inefficient. Okay, so how many cache lines must be fetched before threads can move on? So the takeaway so about caching and coalescing. So again, you want cached access for CPU and coalesced on the GPU. So caching, it's saying what I was telling you earlier. So if thread T is currently accessing at position I, you want its next access to be the next memory position. And to get good access, so coalescing on the GPU, what you want is this, is you want, if thread T is accessing position I, you want the thread T plus 1 to be accessing I plus 1. That's how you will get the most performance out of your code. Not following this principle will cost you an order of magnitude in performance at least. So this is really a big deal. So the rule of thumb, so I was telling you a good thing, if you just remember some simple principle in Kokkos, all the defaults are going to be magic and work for you. And so the rule of thumb here that you need to remember is assume you're working with a multidimensional view and you're doing a loop over some index, you want that index to be the first one. If you follow this simple principle, this is always going to work beautifully for you. You know, when you write more advanced code later, and maybe you do need to loop, you have several kernels and you don't want to change the layout of your data, that's fine. You can control, you have some other level of control in Kokkos, but the thing I would really want you to remember is that if you have the choice, just always have the first index very faster, and then you can use a default view setup, and everything is going to work beautifully for you. So here, so getting back to the inner product, so you got this matrix A of size n and m. So we're computing the dot product for the row I, so it's showing the good access, I suppose. So for OpenMP, you want the thread 0 because the thread 0 is going to compute, is going to do one computational body, so it's going to do a reduction on the first row, so it's going to read all the entries here. So you want this access, and then you want the second thread to be. So you see that maps well like this. And for a GPU, that's the opposite. So the first thread is working on the first row, and that's why you want this different layout, so that the thread have this nice coalesced access. So we were looking at the previous, let me see, unfortunately, anyway, I'll explain what happened. At this data, so you'll get, if you're looking, so it's interesting for this exercise that we don't really have the time to see into depth. It turns out that the way we are accessing the matrix, it's actually, so on the best data, the best pattern will be left, will be left and right here. And for the KNLs, the same thing, you want right and left. Yeah, I got confused. We have other example where on purpose we design a problem where you had to change the layout on the GPU, but it's not this one. I encourage you, if you want to look at this example, to go and look at our online lecture, because we really don't have the time to cover them into details here. And so here, so the summary of this section, so the memory access pattern summary. So every view has a layout, whether you specify it or not. It has one at compile time, and you can select it if you want to change from the default via a template parameter. the most common choices you're going to have are layout right and layout left. The view host space in Kokkos default to layout right, and the views in CUDA space or other GPUs, so heap space or Intel GPU as well, it defaults to layout left. Layouts are extensible and flexible. For good performance, you need your memory access patterns to result in cached access on CPU and coalesced on GPU. The way the Kokkos maps its parallel work indices will work well for the layouts if you have the first argument, the first dimension moving. And so one point that I wanted to bring up here is that with OpenMP or OpenACC or OpenCL, you have abstraction to help you with execution. You can allocate, but you have nothing to help you with layouts, which effectively means that you will, if you really want performance, you will need to have multiple versions of your code, or you will pay the price. And that's one of the great strengths of Kokkos, is that you can actually write your code in a generic way that will have good access pattern both on the CPU and the GPU. Okay, so 20 more minutes? Okay, so I didn't think I would get that far. Perfect. So now, we really saw the core, right? We saw the main parallel pattern, parallel for, parallel reduce, and I told you there is a scan even though we didn't get into detail. And I show you so the execution space to tell where the code execute, memory space to say where the memory is allocated, the view abstraction that help you handle data. We just now went over how the layout will have tremendous impact on the performance of your code. So now I'm going to give you an overview of the hierarchical parallelism in Kokkos. So trying to find and exploit more parallelism in your computation. So this is a bit more advanced, but I want you to be aware that it exists and understand the motivation for it. So the learning objective is I want you to understand what's similar and different between the outer and inner level. So the outer level, you'll see in a minute, and introduce the notion of thread teams and league of teams of thread, and what kind of performance improvement you can get with well-coordinated teams. So let's go back again to our y.ax problem. And so you saw the previous graphs that I glided over that was showing this this good bandwidth that you can reach if you pick the right layout. There's a problem though. You started reaching good performance only when the size started being big enough. So the real question is, like, you need a lot of work to saturate your GPU, and picking the row systematically, the row to parallelize is not going to work very well. Like, to saturate a GPU like a Volta, you need the order of 100,000 rows. Like in your application, maybe your matrix is going to be 1,000 by 100,000, not 100,000 by 1,000, or maybe it's just smaller. So you can't really just with this approach saturate the GPU and get good performance. So now how can we get exploit more parallelism? So that's what I just told you. So first approaches using atomics or using thread teams. So we're going to see, I think, against another attempt to improve the code. I guess we don't give I guess we don't give you the thing. So if you were using atomic, it would be equivalent of doing the scalar integration we saw at the beginning with atomic. So what you would really do, there is the extended version of this slide. That essentially you would have all threads work at the same time. You would have, so every individual an element of the matrix time an element of this X vector, you would have a thread work on it, and then you would add the contribution. But the problem is that you're hammering with the atomics the same location memory, and you're going to get, first off, you're going to get terrible performance just by doing that. In some other cases it might work, but atomics for this problem is a terrible idea. And also, if you start doing that, you're actually going to mess up your memory access pattern. But at that point, you have so much contingency in the atomics that you won't even see how bad your memory accesses are. So it's not really a solution. Conceptually, what you would like to start doing is you want to recognize that for all row, you would like to do in parallel there's reduction. So this take a row of the matrix and do the dot products. You would like to do this in parallel. And that's where so conceptually, that's where you see this is hierarchical work. And so we need hierarchical parallelism to do that. We will try to approach that with thread teams. So now, team policy. So I kept telling you execution policy, but until now you've only seen one execution policy, that was range policy. So now I'm showing you we have more than just range policy in Kokkos. We have team policy, and that's how you use teams of threads. So that the range policy is really your flat parallelism, just a flat loop over a range, where you specify the amount of work. So that's the old signature we saw. So with in Kokkos, when you want to do hierarchical parallelism, we use team policy. So you specify a number of teams, how many teams you want, and the size for every team. And here is how you would construct it. So now your policy is a team policy. Similarly, it has an execution space. You can, just as with range policy, you could omit it, in which case we would deduce that you want to run on the default execution space. And you specify the number of teams. And you'll see in a bit, looking ahead, when you don't know the team size, Kokkos can actually deduce a good team size for you. One thing that I want to mention just here, because I actually don't think I have a slide for that in this, and you could see that in the extended version of the class, is we have another execution policy that we don't cover here, which we call MD range, for multidimensional range. This is really when you have a pattern with tightly nested loops, like where you would typically use in OpenMP. I think it's collapsed. And so in Kokkos, you use Kokkos MD range policy, and you will go towards the hierarchical work when you actually have lines of code between the for loops. Like if you do for I, then you have a line of code, for j, and potentially other things. That's when you want to go to hierarchical parallelism. So it's more generic, but I just wanted to mention there is something more. If you just want to loop over m and n and do something simple, you don't have to use this. There's an easier abstraction to use. Okay, so now the team policy. So now when you're using teams, the functors that you need to provide to Kokkos are slightly different. So what they will receive is a team member. So the type you can get from your team policy, there is a member type, public types that you can get. So what I'm doing here is I'm aliasing member type to it. And so what you need to define is an operator parenthesis, and where you use to take an index for your work ID with the range policy. Now you get a handle for your team that we call team member here. So here in the body, I'm showing you how you can access information. So you can find out how many teams there are by doing you use your handle and you ask for the league size, so how many teams. Which team am I within these teams? You can do league rank. So that's how you would find this information from the handle. And similarly, what's the size of my team and which thread am I on this team. So that's how you retrieve all this information. And so with team policy, so remember I mentioned you don't have any possibility of synchronization on the parallel for. So with team policy, we actually give you, it's still illegal to write your own synchronization mechanism. It's violation of Kokkos semantics, but we actually give you synchronization primitive that you can use within a team, which is team barrier. So we shouldn't be so hard-coding the work mapping. So here I'm seeing again the computational body. We are going back to this example where I'm trying to do the dot products y times ax. The team, so the first approach is if you see, I'm finding out what row I'm going to tackle by looking at which is what team am I. So this problem, I assume what we meant is we're going to launch as many teams as there are rows. One team is going to tackle one row. And so conceptually what we want to do is we want to say do a reduction over all the columns. And then we have a computational body where we are doing the reduction. So we, if that was a parallel, if we weren't inside a team, we would use parallel reduce directly with a range policy, but we can't. But we have the pattern, so we have support in Kokkos to express that it is a reduction, and so here it is. So you have also a Kokkos parallel reduce that you can call inside the body of the computational body in the parallel for over a team. And so what we use first here is a team thread range. So you pass back the handle and you say the range. So there is you want m iteration, and that's it. Then your body doesn't change. And so by doing that, the parallel reduce, so Kokkos is going to take care of the reduction for you. We support parallel for. So in this case, we want to do a reduce. It's a more advanced example, but we have parallel for, and we also have parallel scan since Kokkos 3.4, I think, that you could nest in it. So the mapping of the work indices. So we talked a lot about how, this is going to be your everyday problem. If you want performance, the performance will depend on how you map, and so the mapping we do is architecture dependent. Essentially, we implement things that will give you good default as usual. And the amount of work that we pass in the team thread range here, M, does not need to be a multiple of the team size. So that's one of the great things for writing generic code. So the intra-team reduction is handled by Kokkos. So we're doing the magic of making sure that when you're done with this call, this row sum has a reduced value. So here, let's just look at the anatomy of a nested parallelism in Kokkos. So you always have an outer parallel construct, which can be any of parallel for, parallel reduce, or parallel scan. You hand a team policy where you specify how many teams you want and the size for the team. Optionally, I told you you can tell Kokkos auto, and Kokkos will deduce good value for you. And so then you pass the body of a lambda that you need to annotate with this Kokkos lambda macro. And it takes as an argument a team member. So this optional is because if you do a reduction, you would have a trailing variable for the reduced value. but you don't have if it's a parallel for instance. And then, so conceptually, so you have some code. You could have lines of code before, and then you have a parallel inner, and you can select a team thread range. You give a handle to the build, the size of the range. So here, important thing, the capture. So for inner parallel construct, you're going to capture. You don't need the Kokkos lambda because you're already within the computational main body that's being copied over to the device. So you need to use the raw C++ capture here. So to get the right semantics, to have guarantee that it works, it must compile and run correctly, capturing by value. In practice, when you get more advanced with Kokkos and you want the best performance you can, you could compile with reference, but it's only going to be correct if you could have compiled it, and you'll do the correct result by value. And it's important that you hear what I'm saying, because if you were running on the host and you did by reference, it might work and it's awesome. But then we go to the GPU and we reserve the right to have copies. There might be copies of this guy, so you absolutely can't change them. So that's why I'm saying that semantically you need to make sure it works by capturing everything by value. And so the body here, the argument you get is the index within the batch, and you have your body, and you have the potentially you have the value into which you're reducing if you're doing a parallel reduction. And then all of the body, and it's legal to have to actually have several of them parallel inner next to each other. And I'll see in a minute that you have even a third level of parallelism that's accessible to you with Kokkos. So you can have any combination of for and reduce and scan, but we don't cover scan today. The inner, what I told you. Capture by value is recommended, to make sure you don't accidentally add something that wouldn't be portable. And the policy of the inner lambda need to be a team thread range. You cannot nest a team thread range into another team thread range, but there is other things you can nest. So the first question, what should the team size be? So in practice, I was telling you, Kokkos can decide for you. You can just tell to Kokkos auto, and it will deduce something that works for the backend you're doing. Concretely on GPU, the maximum allowed size would be the size of a block. So on Volta, it would be 1024. But in practice, about the size of a warp, so 32 or 64 on AMD is a pretty good choice. Or sometimes we go a bit bigger. So anyway, you can tell Kokkos to use to deduce it for you, or you can even query. I won't cover it too much, but you can even query for your team policy what would be the maximum size allowed, and you can also query the recommended size. One cool thing that, it's way too advanced for this, but I told you how Kokkos has hooks for profiling, for debugging, and we have something a bit newer for tuning. When you do something like this by saying Kokkos Auto, actually you can enable some the tuning facility, and play with it, and at runtime without recompiling your code and finding something that works well for you. So that's one of the great things about Auto. We don't really work with Intel Xeon Phi much lately, but for the recommended team size would be the number of hyperthreads per core on Xeon Phi. Okay, so an exercise. So here we're getting back to the performance. We had, I think it must be that's the previous result that I was showing you. And we were saying that Oh, that's why I was confused earlier. So the coalesced access was the best as expected on GPU and cached on CPU. And so one of the problems I was telling you was that, well, it only starts being good when you have a very high number of rows. So it would be even higher on Volta, right? And it's kind of a problem because it might not be reasonable. And so if you do the exercise and use nested parallelism here, what you're going to find, and play with the layout, what you're going to find is so we use better the parallelism, and so you see how this shifted. Oh, sorry, this shifted to the left. And the reason why, so first off, so it starts from more reasonable size of matrixing very early, getting very good performance. One thing to note is to the highest count, the performance degrades. But if you think about it, it really makes sense because remember we fix the size. So if the rows start being everything and you go to the extreme and it's just a lot of row and just one column, you're gonna have all the thread in your team just waiting and doing nothing. So that's why it collapsed. It collapsed here. But so the important takeoff was how we were able to shift it to the left. Okay, so how much time? I'm gonna do. I know it should be the break, but let me. Yeah, let me finish that. So so we saw in the exercise you would be seeing the two level of parallelism, but I just want to mention, and I know it's a lot to take at once. As I said, usually this thing you would see on the third day or fourth day, and it would be most of the day this and SIMD and some other abstraction. But I want to mention the third level of parallelism that's accessible. So optional third level in the hierarchy that can be, so you have team thread, and you could have thread vector range as third level. So it can be used for parallel for, parallel reduce, or scan. It maps to vectorizable loop on CPUs or sub-warp level parallelism on GPU. It's enabled with a runtime vector length argument to team policy. There is no explicit access to a vector line ID. You cannot get your ID. You saw that in the team handle how you could know who you are. With the vector level parallelism, you don't know who you are. Depending on the backend, the full global parallel region has active vector lines, which means what this means is potentially you have redundant execution. There is in the extended version. I remember we have a neat example, a small game with Christian show you some bodies of computation. You have to guess what the reduction value is to give you the idea that some stuff can be redundant. But we don't have the time to do it today. So team vector range use both thread and vector parallelism. So here I'm introducing another policy that's called team vector range, and I'm telling you, so it's using both. So sorry, there's two. I know that it's a lot to take in so little time, but there is two. You saw team thread range. There is thread vector range, which is the only third level you can use, but there is a third team level policy that you can use that's called team vector range that can use both thread and vector parallelism. So within a team policy, there are three policies that you can use. Okay, and so now anatomy with 3 level. Again, you have your parallel outer with which is on a team policy. Then inside the body, you could mix. So you can have something parallel middle that would be so parallel 4, for instance, a team thread range, and then you can nest inside it thread vector range, and then you close. You could have another. You could you could have several thread vector range inside the body if you wanted. And then you can have in the body a team vector range. So you can have several of them. So it's very, very powerful what you can do. I want to mention that I told you that we work a lot with our users and whatnot. So in practice, there were a lot of people that were doing an inner MD range, like really regular pattern. So it was tightly nested. So they didn't actually need the fact that they can have a line of code here. And so we are going to add very soon, we're working on that right now, the ability to nest inside it MD range policy. That will be also really a great abstraction added to this third level. Okay. Then another important thing is so the single pattern that you can use to restrict the execution. Like the parallel pattern, it takes a policy, a lambda, and an optional broadcast argument. So there are two policy when you do single, so it's nested again inside a team thread range. So you say single, you can say per thread or per team. You pass a handle to the team member, and you have a lambda that say what code you want to do. And you have the ability to broadcast something to all threads. Okay. I'm gonna go slide over the exercise and give you a summary of the section. So again, sorry, it's more advanced part of Kokkos, but it's important that you know that it exists, and you can get back to it later. So the hierarchical work can be parallelized via hierarchical parallelism, which we have support for in Kokkos. It's leveraged using thread teams that you launch via a team policy. So you saw range policy and team policy now. And I mentioned we have MD range policy. Team work sets are processed by a team in nested parallel 4 or reducer scan via team thread range, thread vector range, and team vector range policy. So there are 3 new team policy that are introduced now that we talk about nested parallelism. Execution can be restricted to a subset of the team, or just to a team, or to one per team or one per thread, by the single pattern that I went over very quickly at the end.